Deep beneath the North Atlantic lies the world's most famous shipwreck, the RMS Titanic. For over a century, bacteria and high pressure have brittled the steel hull into rust. To raise this 45,000-ton wreck, engineers deploy the largest subsea salvage ever conceived. Modern subsea robotics, synthetic buoyancy foams, and cryogenic soil freezing provide the engineering key. Unmanned autonomous ROVs will execute every phase beneath 4 kilometers of freezing ocean. First, high-resolution sonar mapping penetrates deep mud to locate structural load points. Specialized suction dredgers gently vacuum away century-old silt without disturbing fragile metal structures. Engineers designed a custom subsea exoskeleton cradle to encapsulate the fragile hull. Heavy synthetic lifting slings are driven deep beneath the seabed using directional water jets. Buoyancy modules inflated with gas generate thousands of tons of lift on the seabed. Precision hydraulic jacks adjust lifting forces millimetrically, counteracting thousands of meters of water weight. Phase 1 consists of subsea mapping, silt clearing, and installing the exoskeleton cradle. To prevent rusted steel from collapsing, engineers deploy subsea cryogenic ground freezing. Circulating liquid nitrogen freezes the muddy seabed soil into solid ice around the hull. This frozen ice block acts as a protective armor, locking every fragment in place. Subscribe now and comment below on what legendary shipwreck we should raise next. Heavy robotic manipulators secure ultra-strong riser cables to the frozen cradle. Subsea hydraulic tensioning units balance cable load distributions, preventing tilting during the ascent. Syntactic foam modules, engineered with glass microspheres, provide buoyancy at 400 atmospheres. High-pressure water jets break suction resistance between ocean clay and the frozen block. The Titanic breaks free from the Atlantic floor for the first time in over a century. Ascending slowly, autonomous buoyancy controls adjust internal gas pressure as ocean depth decreases. Sensors leave monitoring arrays on the seabed to document the site after wreck removal. Phase 2 is complete, allowing us to examine mid-water decompression and logistics. Phase 3 transit requires continuous pressure regulation as the wreck ascends through the ocean. Automated relief valves vent expanding nitrogen gas from buoyancy bags as surrounding pressure drops. Subsea battery-powered refrigeration units maintain freezing temperatures, keeping the ice matrix rock solid. Escort ROVs patrol the perimeter, monitoring structural integrity and cable tension during ascent. Passing 200 meters depth, natural sunlight pierces the ocean, illuminating the frozen wreck. A specialized heavy-lift vessel submerges below surface waves to receive the salvage cradle. Towed by subsea thrusters, the frozen cradle glides smoothly over the submerged ship deck. Hydraulic positioning arms lock the frozen salvage module onto the deck supports underwater. Submerged ship pumps discharge ballast water, lifting the Titanic wreck above the waterline. Meanwhile, the shattered stern section on the seabed requires a separate specialized salvage strategy. Robotic arms spread steel containment nets over thousands of scattered artifacts around the debris field. Phase 3 is complete. Now we examine stern recovery and preservation chemistry. Phase 4 begins with heavy hydraulic tools clearing tangled steel wreckage around the stern. A multi-segment articulated frame encapsulates the collapsed stern section, stabilizing its crushed decks.
Cryogenic ground freezing creates a second protective ice block around the stern wreckage.
Heavy winches raise the stern cradle, completing the recovery of both major ship sections. Subsea chemical sprayers apply special solutions to neutralize destructive chloride salts inside the steel.
Electrochemical extraction draws destructive salt ions from the iron plates, preventing rapid disintegration.
Precious artifacts are placed inside pressure-controlled preservation chambers deep underwater.
Scientists analyze unique iron-eating bacteria samples, unlocking new insights for rust-resistant marine alloys.
For the first time, the ocean floor returns to its pristine, undisturbed abyssal state. Enclosed environmental climate chambers maintain zero oxygen humidity control during transit. Controlled vacuum freeze drying removes deep pore moisture from the iron hull without causing collapse.
Phase 4 is complete. Next, we examine the Global Conservation Museum and legacy.
Raised from the abyss, the Titanic will be housed inside a state-of-the-art conservation museum. Visitors will stand meters away from the actual hull, preserved in an inert atmosphere.
The salvage investment is recovered through global museum exhibitions, documentary media, and scientific patents.
Every recovered artifact offers an unbroken connection to 1912 history. The massive bronze propellers stand as enduring monuments to 20th century maritime craftsmanship.
Technologies pioneered during the salvage revolutionized deep-sea robotics, subsea mining, and ocean cleanup. Engineers worldwide study the Titanic recovery as the masterclass benchmark for deep ocean salvage. Conquering crushing ocean depths, human determination has brought history back from the Atlantic floor.
This engineering triumph honors the memory of 1,500 souls by preserving their story. From deep beneath the waves, the impossible dream of raising the Titanic becomes reality. Proof that no ocean trench is too deep when human ingenuity leads the way.
These engineering marvels prove that human determination can build thriving civilizations anywhere in the universe.